Chapter 1.3 Geometric Sequences. A geometric sequence is an arrangement of numbers where the ratio between consecutive terms is a constant. Example, let's pick a number to start. I'm going to pick the number 5 to start with. Pick a number to multiply by. I'm going to pick the number 2, and then write our sequence. First term is 5, second term is 10, third term is 20 because we're timesing by 2. Fourth term is 40, fifth term would be 80, and so on. The number we start with, that's our T1. The number we're multiplying by, that is called the R value, which is the ratio between consecutive terms. And we can see that it's the ratio if we take R equals T2 divided by T1, which would be 10 divided by 5 equals 2. Or we could take R equals, let's say, T5 divided by T4, which is 80 divided by 40, which also equals 2. Let's do another example. I'm going to start with negative 10. And I'm going to have an R value of 1/2. Then my first value in the sequence is negative 10. Multiply that by 1/2, I get negative 5. Multiply that by 1/2, I get negative 2.5. Multiply that by 1/2, I get negative 1.25, and so on. And we can check that our R value is 1/2 by finding the ratio of consecutive terms. So if I do R equals T2 divided by T1, that's negative 5 divided by negative 10, which is positive 1/2. Or we could do T4 divided by T3, which is negative 1.25 divided by negative 2.5. I'll use my calculator for that one. Negative 1.25 divided by negative 2.5 is 0.5, which is 1/2. The general term of a geometric sequence is Tn equals T1, the first term, times R to the power of n minus 1. So T1 is the first term n is the term number, R is the common ratio, which is equivalent to the ratio of two consecutive terms, so T2 divided by T1, or T5 divided by T4, or any two consecutive terms, so Tn divided by Tn minus 1, and Tn is the nth term. Example, find the general term and the 12th term of the sequence 3, 15, 75, 375, etc. Let's start by writing down what we know, just like we would do for an arithmetic sequence. T1 equals 3. R equals, take two consecutive terms, so let's say T2 divided by T1, which is 15 divided by 3, which equals 5. So R is 5. Tn, the general term, is something we want to calculate, and we also want to calculate the 12th term, T12. Start with the formula for the general term. Tn equals T1 times R to the power of n minus 1. Tn equals T1 is 3 times r is 5 to the power of n minus 1. We can't simplify that at all, so that is our general term for this sequence. A note here, 3 times 5 to the power of n minus 1 is not equal to 15 to the power of n minus 1, because we don't have an exponent of n minus 1 on the 3, so we cannot multiply those two bases. So this is how it should be written. And do not do this. And then we want the 12th term, so T12 equals 3 times 5 to the power of 12 minus 1. T12 equals 3 times 5 to the power of 11. And then we calculate. Three times 5 to the power of 11 is a large number. T12 equals 146,484,375. So 146,484,375. Suppose there were 3 bacteria originally present in a sample. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. State the values of T1 and R. So T1, the initial amount of bacteria was 3, so that'd be our first term. It says determine the general term that relates the number of bacteria to the doubling period. Since we're doubling, that means our R is equal to 2. And then we want the general term, Tn. Tn equals T1 times R to the power of n minus 1. Tn equals, T1 is 3 here, R is 2 to the power of n minus 1. So there's our general term for this sequence. Suppose the smallest reduction a photocopier can make is 60% of the original. What is the shortest possible length after 8 reductions of a photograph that is originally 42 centimeters long? So our T1, that would be the starting measurement of the photograph, which is 42 centimeters. Then the R value, the reduction the photocopier can make is 60%. When we have percents, we want to change them to decimals. So that'd be 0.60. The copy will be 60% the size of the original. So R is 0.60. We want to know what happens after 8 reductions. 8 reductions would actually be term 9, because term 1 is not a reduction. Term 1 is the original. So then term 2 would be first reduction. Term 1 equals original. Term 2 equals first reduction. Term 3 would be second reduction, etc. So we have the term number is 1 more than the reduction number, so then term 9 would equal the 8th reduction. Then our general term, Tn equals T1 times R to the power of n minus 1. T9 equals, T1 is 42, R is 0.6 to the power of 9 minus 1. T9 equals 42 times 0.60 to the power of 8, and then we calculate. (42 times 0.60 to the power of 8. That gives us T9 equals, we'll round to the tenths place, so 0.7 centimeters. That would be the length of the photograph after 8 reductions. In a geometric sequence, the second term is 28 and the fifth term is 1792. List the first 3 terms of the sequence. We know that T2 equals 28 and T5 equals 1792. Let's start with the general term. Tn equals T1 times r to the power of n minus 1. We know the value of T5, so let's do T5. Term 5 equals T1 times r to the power of 5 minus 1. And we know that T5 equals 1792. So where the T5 is, I'm now going to write that number. 1792 equals T1 times r to the power of 4. I can rewrite T1 times r to the power of 4 as 1792 equals T1 times r to the power of 3, right? R to the power of 4 is just r times r to the power of 3. And then we have term 2, and term 2 is just T1 times r by the definition of a geometric sequence. So that is term 2, but we know the value of term 2 is 28, so we can plug that in. We get 1792 equals 28 times r to the power of 3. Now we can solve for r. Divide by 28 on both sides. 28 divides out on the right. 1792 divided by 28 is 64. 64 equals r to the power of 3. We want r, so cube root both sides. Cube root of 64 is 4. Cube root of 64, we get 4. So r equals 4. Next we need to figure out term 1 so that we can get term 1, term 2, and term 3. We already know term 2, that's fine. So we can either plug r equals 4 back into this to figure out what T1 is, and then use that to get from T1 to T2, which we already know, to T3, or we can just use multiplying and dividing by r. So we have term 1, term 2, and term 3. Term 2 is 28. To get from term 2 to term 3 in a geometric sequence, we multiply by r. R in this case is 4, so multiply by 4. 28 times 4 is 112. And to get from term 2 back to term 1, instead of multiplying by 4, we would divide by 4. So 28 divided by 4 is 7. Then we have that the first 3 terms are 7, 28, and 112. Give the value of r for the following situations. A. a population grows at a rate of 3% per year. If something is growing, the R value would have to be greater than 1. 3%, if we have percent, we want to change it to a decimal. That would be 0.03, but that is less than 1%. That would mean a decrease in population, not an increase in population. So if it's growing, we have to add 1 plus that percent. So we get R equals 1.03. And note that the 1 as a decimal is equivalent to 100%. So this means the population next year will be 103% of what it was this year. Next one, a population shrinks at a rate of 8% per year, so it's decreasing. That means it has to be less than 1. Our percent is 8. We want to change that to a decimal. That'd be 0.08. Now we have to be careful with this. Our population is shrinking at a rate of 8%, so if we want to know what's remaining, that would not be the 8%. That would be 100% minus the 8%. So for the R value, we have to do R equals 1, which is 100%, minus 0.08 or 8%. That gives us R equals 0.92 or 92% of the population remaining. A house appreciates at a rate of 13% per year. Appreciates means the value is increasing, so greater than 1 since we're increasing. It appreciates at a rate of 13% per year, so as a decimal that's 0.13. Then R equals 1 plus 0.13, so R equals 1.13. A car depreciates at a rate of 23%. Depreciates means it's going down or decreasing, so we'd have to have an R value less than 1. 23% is 0.23 as a decimal. That's how much it goes down by, so the remaining value would be R equals 1 minus 0.23, which gives us R equals 0.77. And again, that would be the amount remaining. In 1990, the population of Canada was approximately 26.6 million. The population projection for 2025 is approximately 38.4 million. If this projection were based on a geometric sequence, what would be the annual growth rate? What assumptions did you make? They give us the initial value, which is T1 equals 26.6 million, and that was in 1990. And then we have another term, which is in the year 2025. That would be 35 years after 1990. So term 1 was 1990. Add 35 to that. That would be term number 36 is 38.4 million. And that was in the year 2025. So figuring out the term number, especially if it's number of years, you really have to think about what the term number would be. If you don't put too much thought into it, you might think it's term 35, but you have to remember that term 1 was in 1990. So if we add 35 years to that, that gives us a 2025. We have to add 35 to the term number, so 35 plus 1 gives us term number 36. Then we're going to use our general term formula, Tn equals T1 times r to the power of n minus 1. And we're going to do term 36, which is T1, which is 26.6, times the r value, which we don't know, to the power of 36 minus 1. But we know what the value of T36 is. It is 38.4 million, so that equals 26.6 times r to the power of 35. Then we can divide both sides by 26.6. .6 divides out on the right side. .4 divided by 26.6 is 1.4436 ... equals r to the power of 35. And we want r, not r to the power of 35, so we have to take the 35th root of both sides. Math, choose number 5, and then I put the 35 in for the index, and I'm going to do second answer to plug in that last answer I calculate, and I get that r is equal to 1.0105 ... Now remember that if we have a growth rate, which we do here, it says growth rate, that means it has to be greater than 1. So we take 100% and add the growth rate. When we change that to a decimal, that becomes 1 point something. So this represents the 100%, and this part is the growth rate. Times it by 100 to change it back to percent, which moves the decimal 2 times to the left, which gives us a growth rate equal to 1.05%. And what assumptions did you make? So our assumptions that we make would be that the growth rate remains constant throughout these years. That brings us to the end of Chapter 1, Lesson 3.